Hello. Anybody here has an ID or IDs sometimes? I'm here to talk about that a little bit. So what happens when an ID is born? First, we think about it, and we get really excited that we get this idea. If we're a good scientist, then we implement it in a notebook. We start exploring. We want to make sure that this idea is working as expected, like we thought. It's going to make the world a little bit better. We see that it does make the world a little bit better, so we put it in a module, a Python module. We can run it on our CLI, not only in a notebook. Maybe we can create a pull request, have our friends clone it. But now we want everybody on the internet to use this idea, so it has to become a server, a service, something useful. So we need the help of an engineer. The engineer is kind of overworked, but he also likes good ideas, so they will help the scientist to make their idea into a service, a useful service. But the scientist and the engineer, they are really, really busy. So once the service is ready and it works on their machine, they throw it over the wall to the SRE, because that's his problem now. But the SRE has a lot of work to do, and he doesn't know about the idea. Maybe he doesn't even care about the idea. So the world didn't get better because people didn't get to use our ideas. They didn't get to use the service in the right time, and once it was exposed, it was already too late. We don't really care about it anymore. We couldn't validate that the ID was good. So is there a better way? Let's have a look. What happens when an ID is born? We think about it. Maybe put it on the whiteboard. We turn it into a service, deploy it continuously. The world got a bit better because a lot of people use the service. We use the Darwinian process to make sure that only the fittest service survives. So we put a lot of work into the good ideas, making them useful. So what I think we need is that data scientists, they should have full control over the solutions they implement. It's not just an idea anymore. It's not a model. It's a solution. So it's a move to useful solutions from brilliant ideas. Everybody has brilliant ideas. Not everybody can make them useful. At first, do scientists even need DevOps? I mean, we just pay them for their brains, right? Not anymore. Just like you can't say it works on my machine anymore, you're not a developer if you don't know how to deploy. I don't think you're a scientist if you don't know how to make a useful solution. Not data scientists. So frustrations are shared in the teams. Everybody wants to be on the cutting edge. Everybody wants to have an impact. Nobody likes to wait. Nobody likes long build times. Everybody wants to innovate. They want to have impact on their own project. How can you make sure there is a feeling of ownership if the distance between idea to a service is so large? I think you can't. So shortening this distance will make our work better. Because priorities are not shared. The different roles, they care about different things. Engineers may care about performance. Scientists may care about gradient descent or other algorithms. And a lot of DevOps folks, they talk about observability and monitoring and security, maybe. So how do we make everyone work on the things they like, on the things they are best at? Separation of concerns. So Let's see how we did it. What really prompted me to implement the Asaf platform is the last Flask app in Wunderkind. It has 5,000 lines of code, and only 5 lines are the actual model. Everything else is data validation, data cleaning, maybe some error reporting, logging, all sorts of boilerplate. Now, the problem there is it's nobody's project. The scientist, well, it's only like a tiny percentage of his code there. The engineer, that's not really her project either. She just wrapped a model. Does she even care? No. Let's let the professionals work on the professional field. So Asaf, it's a simple model-serving platform. It offers a single library import that transforms any function into a high-performance server. I implemented it with Docker in mind and Kubernetes, basically distributed operating systems. If you use those, you're going to have a really good time. So the main premise is taking any function and with a single import, transforming it into a server. Now, if we have the same library exposing all of our models, then all the improvements can be shared. So Asaf automatically passes the function arguments from a URL option string. It does automatic JSON marshalling, and it also allows easy horizontal scaling if we're using a distributed operating system. It's a bit complicated. Let's see how it works. I'll set it up a little bit. This is Bob. Bob is profile 201. Bob likes a recommendation about a movie. As a scientist, I like to create recommendation systems, so I think I may be able to help Bob. In my database, in my training set, I know that Bob likes historical war epics. He also likes romantic comedies, especially When Harry Met Sally. I also know Bob doesn't like Akira. But my big question is really like La Femme Nikita. I'm really interested in that. So let's implement a recommendation system. I'm using a library called Surprise. The training function loads the movie dataset. We use the k-nearest neighbor algorithm to fit it. I implemented this function. It takes an algorithm, returns the function, so it's queried. We do take the profile 201 for Bob, or 101 for Alice. And if we want to train online, we can also pass the actual user rating. All right. Let's see if this works. All right. So we get a bit of a printout. It says estimated user rating 4.3. Great. We have a recommendation system. But how do I know if it's even working? How do I know if it's useful? I need to have my colleagues use it. I need to have other users use it. The more people will use it, the more data I will have, and the more I will be able to verify that this service is useful. All right, so let's put Asaf into it. It's exactly the same. This is where we got our printout, and I'll uncomment the import. We call start. That's the Asaf entry point. We pass an empty config and our function. All right? So our function is predict, and now it's exposed as a service. Let's have a look. So I'm running the front end locally. It's a distributed system. want to take a look at the Asaf config, if you don't mind. Just notice the return key, it says estimated rating, and the queue name is recommend. Now, I run my Python script just like before. This is a server now. We get the same printout because I didn't remove it, but it's waiting. And we can make a request. We get something in return. I think it's really great because zero boilerplate, we get a high-performance server. We get the JSON marshalling, like I promised, so we can see the estimated rating mapped exactly from the config. We can also look at the curl request. It's localhost 8080/recommend, just like the queue. So the scientist will choose the path and the arguments. So, La Femme Nikita got 3.8 out of 5. I would recommend Bob to watch. It's a pretty good movie. So again, Asaf transforms any function into a server. Let's take an abbreviated look at what we just saw. We have a function. It's predict. It takes a profile and an item idea. We have a config file where we define the return key, our RabbitMQ configuration, and the queue name, which automatically maps to the path. We pass it to Asaf, and we get a response in return. The scientists doesn't have to think about it because they don't care. Engineers do care about marshalling, about schemas, so they can control those. And for the DevOps people, if you know how to deploy anything on Kubernetes, you know how to deploy this, because it's just a Helm chart and a container. So finally, we can give continuous deployments to scientists. It looks pretty traditional. We have a scientist, we have an engineer. They push into GitHub. The approved pull requests are picked up by drone. The build tool builds the images, runs the tests, which scientists also have to write because the services are exposed. People use it. There's concrete proof that their algorithms doesn't work, so they have to fix it. And there's a special separation because only their code is running in that service. It has to be their responsibility. Which means scientists in triage. Letting scientists fix their bugs makes them realize what it means to work in IT. Many of them have academic backgrounds or no backgrounds, and they're brilliant, but they still value ideas a lot. They don't go through the fire and flames that engineers sometimes had to go through, those lamp stack installations at 3 in the morning and stuff like that. So it was very important for me to scrape the boilerplate. When we scrape the boilerplate, we can make sure that the people are concentrated on what is important. So how did we do that? How did we make DevOps easy enough for even a scientist to understand? We have a few base repositories. We have a Python module structure. It has the init files and the directory structures that the scientists can clone, which fits really well with the Docker file they can clone. So only some changes are needed in that file. The build file for drone is also very straightforward because the interface is cohesive. Not a lot of changes are needed there. And in the deployment file, the kube YAML, there are usually no changes needed at all. A tiny example. On the top, we can see the Docker file and the Wonderkit database Docker image. It has the Asaf dependencies like 0MQ. In the middle, we have the cube YAML file, which drone passes the double squigglies into. So if the scientist knows how to call their image, it should work. And it is. So that's our infrastructure. This should already be quite familiar. On top of Kubernetes, we have an HTTP server. It's written in Golang. It's just a container. If you can deploy any container, you can deploy that as well. The request queues are currently implemented with RabbitMQ. The Helm chart for that is very helpful. And then we have connectors. It's what we just saw, that the Docker file is deployed via drone. The connectors pick up the messages from the request queues into the models, and then the models put them in return. So it's a very simple system with ready-made products that we all already use. It's important to realize that trained models are just files. Right now, we have great success training when building the Docker file. So drone itself, we persist all of the training data, we load the training data, and while building the Docker file, we train, and we have the latest trained model right in the Docker file. Distributed. We can also use rsync if we really want, if we really, really care about continuous updates of our model. And if it gets so good and so useful that we need continuous updates, we can move to TensorFlow. So now I want to talk a little bit about the design decisions implementing the SAF platform. If you want to use it, you might not care. If you want to contribute, I hope you will care. So, RabbitMQ message queues. They decouple the producers and the consumers. It was the main objective was this decoupling of the engineering efforts and the scientists' efforts. It also gives us out-of-the-box resilient communication. We see that even if the model is not online and the message was sent, it will wait in the queue until it gets picked up by the model. And of course, it's language agnostic, because if you can connect to RabbitMQ, you can connect to a SAF. You might have to write a connector if it's not Scala or Python. HTTP over queues seems like a solution that many companies converge onto. There's the Hermes project, which is really nice on Kafka, but it's a bit more complicated. It's directed at engineers. This is directed at scientists. It has to be very simple. So it's high performance, it's resilient, it has observability out of the box. I didn't show you Jaeger at the demo because I think you already saw enough tracing, but it's already instrumented with Jaeger, and we have cache. Because we have only one entry point, it's very easy to wrap services around it. Another important decision was to use only message passing for concurrency. Even concurrency professionals don't really want to use concurrency, so people who are not professionals, that definitely shouldn't think about it. Green threads, threadlets, greenlets, not here. In Go, we use channels. In Scala, we use actors. For Python, we use ZeroMQ. It's a simple implementation of message passing. It's fast, it's reliable, and it's much easier to reason about than locks or semaphores. Because it lets us write embarrassingly parallel applications. We write procedural, run it in parallel. As long as requests are atomic, we have high availability out of the box and infinite horizontal scaling. On the first day, I got a message on Slack. Some things were slow, scaled up one of our services, and everything was OK. If you want to implement an ASAF connector, it's pretty simple. You asynchronously pull the messages from the RabbitMQ queues. That's the ASAF connector's job. These requests are being passed to the model. The model blocks when the request finishes, it goes back into the response queue, and the next message is ready. We have almost no overhead in our performance testing. We have some future plans. I want TensorFlow integration. I think that would allow even greater implementations of ASAF models. Right now, we mostly support scikit-learn and derivatives. A Helm chart will make onboarding a bit easier. Right now, you have to really know what you're doing and how Kubernetes works, which you already should. And more instrumentation. The Elastic APM is a big target, and so is Prometheus. So, the benefits of using ASAF. It allows teams to focus on what matters. It has observability out of the box, and most importantly, it allows a Darwinian development process. Only the fittest service survives. You know that it's the fittest because the most people use it, and the more people that use it, the more fixes you are going to put into it. The better it's going to be, the more useful it's going to be. If you want to contribute or if you want to use ASAF, please visit GitHub. It's /the platform. You can follow me on Twitter. I post pictures of cats sometimes and my thoughts about meditation. If you like the art, follow Daryl De Picciotto. That was me. Thank you very much.
Thank you, Ram. Hold on a sec, because the guys with the mics are coming. So, first of all, any questions?
The first question should be, how do I start using ASAF? Thank you for this question. You start using ASAF by cloning. The project looks in alpha stage. It's not super clean, but it's very resilient. It works really well. So now it's the great time to start contributing. Very open to suggestions. The Helm chart, contribute a Helm chart. That would be really, really great.
Questions? No questions? Looks like there are no questions. Well, thank you, Ram, and enjoy the coffee break.